talking about effective QCD phase diagram as soon as he gets the pointer.
Great, thank you.
I'll let you know with 5 minutes.
Okay. Well, I can start by thanking to the organizers for the support given and for the great organization of this event. I see. Uh, so I will talk a little bit about the same stuff that Luis Hernandez talked before. We'll talk about the QCD phase diagram using the linear sigma model, but I will focus on studying the speed of sound. But first, I want to invite you all to the next meeting of the second Latin American workshop on electromagnetic fields effects in QCD that will be happening on Santiago the last week of November, 24 of November and 28. So please visit the website, have the information that you need for them. And also, this event will be at close to another one that will be announced by Christian, which occurs the next week after this one, which is the QCD perturbative, I don't remember exactly the name, not perturbative matter or something like that. Well, to the outline, first I will talk about the motivation on studying the QCD phase diagram. Then I will introduce the model that I will use to do that. I will announce some results of what have been done in the past 3-4 years, and some comment of what we learned from that. And then what I like to do next, once that we have some knowledge about the things that we can and we cannot do, and then how I will use that to study the speed of sound. So the motivation, I mean, I think that we all talk a lot of this in the whole week. QCD under extreme conditions, temperature and finite density plays an important role to understand the transition that took place in the early universe. We can find that kind of conditions on the heavy ion collisions and in neutron stars. One of the goals is to try to understand how these transitions occur, either confinement or the chiral restoration. And we usually use this kind of phase diagrams to announce the result that we have. But the reality is that nowadays we actually don't know a lot of the things from this phase diagram. We are only sure about things at low chemical potential and very high temperature. Of course, there is some experiment efforts to despite these doubts at higher densities. Experiments like NICA, PES2, and JPark and Alice. So what I'm going to use to try to dissipate these doubts is the all reliable Mexican hat potential, or you can also refer as the bottom of the Mexican Coke. So we will use that tool to try to focus on studying the chiral symmetry by using the linear sigma model, which is an effective model for low energy QCD, where we have quartz and meson, and we will focus on how the chiral phases transition occur. This allowed us to implement chiral symmetry and spontaneous symmetry breaking very easily. So this is the Lagrangian after we allowed the spontaneous symmetry breaking of the linear sigma model, when we can identify the masses for the sigma, the pion, and the fermions, in this case quarks. And then we have the interactions that allow us to develop our theory. And then, because we allow the spontaneous symmetry breaking by using the order parameter, will be the B, and these masses will increase with the order parameter of the transition. So in order to study the criticality, we will use the effective potential, particularly to one loop. We will use the effective potential for fermions, for bosons at one loop, and we are going include the media effects, but include the corrections to the ring diagrams in the boson contribution. That then, if we have all on account, we will have the classical potential, the boson one loop, the one loop of the boson, the one loop for the fermions, and the ring contribution. And we are calculating all these contributions together, and that will give us the effective potential. In particular, the ring contribution will be, and the whole potential will be calculated at high temperature. Given this means that the self-energy will give by this expression that corresponds to the whole correction for the rings. And this is all the contributions to the self-energy. Then, if we put all together, we will have the effective potential for the high temperature approximation. This is the 3 level of the classical contribution. Everything else is the boson and the fermion one loop correction, and this is the only contribution given by the rings. So now that we have this, we can try to fix the parameters for our model. And the main goal here is to use something that is phenomenological, meaning that we need to not just give numbers and try to see what happened. So try to use some observables or something that is really reliable, like lattice QCD. So what we use in this work from 2020, in this work from 2022, is we are going to use the critical temperature given in lattice QCD in this work, and the curvature as well for the lattice results. So we will use this parameter K2 and K4 to find the A and G parameters that guarantee that the curvature of my future phase diagrams have the same curvature for low chemical potential. That's the one in lattice. And also to secure that the critical temperature at 0 chemical potential is the same as lattice. So then we have 2 of the parameters fixed, and we have the other one free, which is lambda. But even then, we can see that lambda is kind of reduced free parameter space, because if we go higher than 2 for lambda, we have masses of sigma that are really too big. That doesn't make that much sense. And also we cannot go lower than 0, right? So this is like the most reduced space of parameters that we have by 2022. For this combination of parameters, what we obtain, for this range of lambdas, what we obtain is that the critical endpoint should be in this window. This is just an example of a phase diagram for this special set of parameters. And we can see that in our model, because we are working at high temperature, we are limited into how low we can go in temperature. And this is the most of the first order transitions points that we can obtain. But still we will be able to obtain some critical endpoint. So that's what we were in 2022. So what now? Well, what I want to do is to use the speed of sound, which is close related to thermodynamics properties of any system that includes an equation of states. For example, the speed of sound is recently very used on the studies of neutron stars, because the behavior of the speed of sound can tell us about the change on the baryon number density and had an influence on how the mass and radius relationship can be reproduced. Also, in heavy ion collisions, the speed of sound can give some relevant information. For example, it displays a local minima in the crossover transition at 0 chemical potential. So what we can try to do now is to calculate the speed of sound, the square of the speed of sound for our effective potential using the definition of the speed of sound, when this high denotes the parameter that will be keep fixed by doing this calculation, and depending on what kind of parameter we keep fixed, we will have different properties of the propagator media. For example, we will just focus on using the speed of sound at fixed density, at fixed entropy, and a fixed ratio of entropy and density. And this is how we will obtain the expression for the speed of sound in our approach, But notice that the effective potential is not other thing that's the negative of the pressure. We will have this relation for the energy, and we can obtain the entropy and the density by this derivative of the effective potential in terms of the temperature or the chemical potential. And we can obtain as well the susceptibilities by derivative of mu and t. So all is reduced to calculate derivatives of mu and t in b equals 0 of the effective potential. So once that we can do, we are able to calculate the speed of sound. The speed of sound, I want to use that as a way to fix the parameters in another physical observation. For example, we can use the fact that at the critical temperature at zero chemical potential, the speed of sound presents like a minima that is around the value of 0.15 and 0.16, and use that results from lattice and from the HRG models as an input for our model. This is another results from the speed of sound in different works. And all of them have the same behavior. You have this minima, and there is always around 0.15 and 0.16. So now I will use that to fix the same parameter as before, to fix the critical temperature at zero chemical potential, the curvature for lattice. But now I will study two cases, the two-flavor case and the three-flavor case, with the respective critical temperature. And this is what I can show now as the possible value for lambda. This is just like the previous work. I didn't use the speed of sound yet. And then what I will use is how the speed of sound changed by the parameter lambda. And we can notice that for the three-flavor case, we are not able to reach the value of the speed of sound that is shown in lattice, but for the three-flavor case, we can do. And so what I did is I choose to use the minima, or the closer one, and then the one that crossed the actual value. And with those, these are the lambdas corresponding to that explanation that I just gave, and I can reproduce these two phase diagrams. The blue is the one that used the critical temperature of the two-flavor case, and the purple one is the one that used the critical temperature for the 2+1 flavor case. And then you can see that only one of them it's allowed by the limit of our expansion, the high temperature expansion, to obtain a critical endpoint. But still, we can have some additional information from it. For example, we can use the speed of sound as a criteria to try to see the behavior around the critical endpoint. As we can see here, the speed of sound decreases rapidly around the critical endpoint. So for the future, what I want to do, or what I'm trying to do now, is to build upon previous studies that incorporate magnetic fields into the linear sigma model to investigate the behavior of the speed of sound along and close to the transition line, and try to see if there is any signal that can give us some insight of the behavior of the catalysis, magnetic catalysis or inverse magnetic catalysis. And that's all. Thank you for watching.
Okay, thank you. We have time for a couple questions. Yep.
Thank you, Saul, for the talk. When you feed the lattice results to feed the couplings, yeah, but these are results depending on the. I see. So this is the result for low for low
Zero chemical potential.
chemical potential
chemical
expansion in or because they are results with Taylor expanding
Yeah.
chemical
So
potential.
for this converter, you have a small expansion, but still you cannot go really high on chemical potential.
Yeah, that's what I mean. But this is what you use, the
Yes.
chemical potential expanded in Taylor.
Yes.
Yeah.
Until I would say like around 30 MeVs or 100 MeVs, something like that.
Yeah, but this expansion is assuming high temperature. So just pick this and try to mimic this, and your couplings are temperature dependent or not.
I fix them on this condition, but they don't change. One that I fix, they don't change with the temperature.
Okay, neither the barium chemical potential.
No.
Okay. Okay, thanks.
Thanks. Any other questions? Let's come up here first.
Nice talk. Have you calculated the trace anomaly in this case? Because normally we calculated fixing the entropy per barium, but now you are defining it in another way. Maybe this will influence to the trace anomaly, because normally it is positive at finite temperatures, even if you add chemical potential. But maybe now with this definition could be different. Have you calculated it?
No, I didn't calculate in that way, but still we can try to do it in the way that you mentioned. And the only thing that we need is we need to be able to calculate the, what is the word again? Susceptibilities, and that's all we need.
Okay, thank you.
So there was this concept of quarkionic matter with the peak of the speed of sound.
Yes.
With your model, can one get something similar or not?
Mm-hmm. So so we can have some peaks in the speed of sound, but
At
those
mu
are
B, at mu B, which is of the
but
order
not
of
at
like
mu B.
1
I mean,
barium per barium.
So
Yeah.
what that peak means is that you have this transition, that you possibly have this transition on some quark matter and some nuclear matter, maybe. So that might be one explanation, of course. But you can have peaks of the speed of sound just by the fact that you have a first order transition or a yes, a deep one is a first order transition, or a soft one if it's a second order transition. But yeah, I mean, if you can try to find a sector of the of temperature and chemical potential that you are a specific one to study, then you might have something like that. But you will need to introduce a transition in some way, I think.
Okay, let's thank Saul again. Let's see, our next speaker is João Paulo Sampaio Santos. And I don't have the title because it's not online. The last day is not. Okay, superconductivity and confining models.
Hello. Thank you. Okay. I would like to thank the organizers for the opportunity to present my work here. My name is João Paulo. I'm a PhD student at UERJ, and I will present my work with my advisor, Letícia Palhares, about superconductivity in confining models. So, first of all, I will introduce to the audience some mainly concepts about superconductivity or superconductivity in high energies, and after that, I will give a very fast talk about the confinement, because Letícia has already introduced this topic very well 2 days ago. And I will try to explain how this confinement ingredients can affect the superconductivity in this scenario. Okay, in the beginning, the superconductivity is a phenomenon from the condensed matter discovered more or less 100 years ago, when Hank Camerlions cooled mercury with the helium liquid below some critical temperature, and the material didn't present any resistivity. And conversely, this material present a kind of supercurrent. But more or less 50 years later, that a very well microscopic theory was developed to describe what's happened with the material. What's happened is that below some critical temperature, the electrons in the usual superconductivity can interact attractively, scattering with the modes of the vibration lattice that column follow. This generates a stability close to the Fermi surface, reorganize the system in a new ground state based on the new quantities called Cooper pairs and the usual superconductivity. This ground state is formed by two electrons that interact attractively. A very important thing that happens is that this collective phenomenon present a kind of quasi-particle dispersion relation with this space here, that's the superconducting gap, that is the quantity that blind the system through the thermal fluctuations or another kind of energy. So to return to the fermionic system without superconductivity, the system has to receive a kind of energy to destroy the superconducting gap. So that quantity is one of that we are interested in investigating this work. The color superconductivity is the well-established model of superconductivity to study in the high energies. It happens in this part of the phase diagram with low temperature and medium or very high chemical potentials. And in this case, the Cooper pairs are formed by the quarks that interact attractively, do the strong interaction, exchange one gluon. So the idea of this work is try to understand what's happened if we replace the usual gluon propagator by a propagator of some confinement theory. So I will pass a little bit fast about this topic, but I have to comment some points. In the quantization of the gauge fields, to avoid overcounting problem, usually we apply the procedure of the Faddeev-Popov. We apply the Faddeev-Popov procedure, and these are the Grassmann variable, the Gauss, the Faddeev-Popov. And this quantity is the determinant of the Faddeev-Popov. And after applying this procedure, is it possible to fix this overcounting problem, correcting in the action with the new term that is the gauge fixing term. And this guy here is the determinant that could be exponentially put in the action. This procedure is well established in the literature and work through all orders in perturbation theory, but in the ultraviolet limit, but in the low energies has a problem because this determinant can present zero modes, what spoil all the procedure. The zero modes are related with the possibility of this field's configuration be counted more than one time, generated the Gribov copies. So Gribov, in a very smart way, restrict the domain integration of these fields, being possible to compute some quantities. For example, the interest of this work, that is gluon propagator, that if we analyze the partial fraction present imaginary poles in a way that we can try to explore these imaginary poles, try to understand the gluon as a particle that are out of the spectrum of the theory. In 2007, with some simulation of lattice QCD at low energy, the people showed that this gluon propagator present a kind of saturation close to the infrared limit. So the Gribov-Zwangsger theory was refined, and here your propagator now present a shape that agrees better with the lattice simulation. This is the RGZ, or refined Gribov-Zwangsger propagator, where these mass parameters are related, are computed from the lattice data. And the last one model that we will explore is a propagator extracted from the Curti-Ferrari models, when the gluon present an explicit mass term related some phenomenological aspects of the young muse in low energy. And we try to explore the deep infrared part of this model through the running couplings of this model that can be computed from if a kind of specific renormalization scheme, that the infrared scheme, through the equations from the renormalization group. So the model can be modeled in the first part of the work in a simple way by a fermionic sector, in a more simple way in a single fermions with one color and one flavor, without putting in count the spin. The bosonic part by a scalar Hell field, in a way that will be possible compute a kind of propagator that similar with the Gribos-Wansger, and Yukawa interaction, and was reproduced the usual computations of the superconductivity with quantum field theory. First part, we integrate out the gluon fields, and we get action only in the fermions, the Dirac fields. And the next step is made a mean field approximation. And to make the mean field approximation, we have to introduce the fermions with conjugated charge, when DC is the charge conjugated matrix. And applying the mean field approximation, considering fluctuations close to the mean field in first order, is it possible to get this action with the new fields that we can call of gap function through this quantity that we will be compute the superconducting gap. All the procedures is very new. It will be possible to rewrite the action in a new spinor base, and they call it Nambu-Gorkov space, a kind of bidimensional space where the out of the diagonals, the anomalous propagator, are our gap functions. So that's a diagrammatical way to see this gap function. And maybe a Fourier transformation will be possible to compute the superconducting gap, replacing this guy by the confining propagators. So first of all, we needed ansatz to solve this self-consistent equation. That's the ansatz that respects some properties. We suppose that the gap is a real function, and fermions with the same chirality, and fermions that respect the antisymmetry with exchange of the fermionic fields, and in spin singlet pairing, based on the Bailin-Love work, and Pisarsky and Hisk also. And we reproduce the same computations based on the computations made by Wilczek and Schaffer work in the color superconductivity. So we consider the zero temperatures approximation, so it exchange from the Matsubara summation by integral in the Euclidean. And we consider that the system are in the vicinity of the Fermi surface, so the gap depends only on the frequency, and the momentum can be separated in a part of the Fermi moment in the Fermi surface and another orthogonal to the Fermi surface. And it will be possible to get an integral gap equation very similar with the QCD guys obtained some years ago, but with the additional ingredient that the explicit mass parameter that are related with our confining propagator. So is it possible to expand? Is it possible to expand this nonlinear term and also obtain approximate equation? So analyzing the results, it's very interesting that how large is this mass parameter? The superconducting gap that in principle is a peak close to the small frequency become a flat part here, and this plateau is give rising how large is this mass parameter. This result is the approximate result from the approximate gap equation. But when we solve the integral gap equation, we understand better what this mean, because how large is the mass parameter? Small is the superconductivity, smaller is the superconductivity in the system. Here there is a comparison between the integral solution, the approximate solution. So there is a good agreement to the high frequencies, but in the frequency, to the small frequencies, there is a deviation here. With analyzing the case with the RGZ propagator, the gap still with a small veil. This small veil is based because all the lattice parameters, the mass parameters extracted from the lattices are are bigger than the chemical potential. But if you increase the chemical potential of the system, you will see that the superconductivity becomes more relevant in your system. Here, the first is the result of the gap divided by the chemical potential, and later is the superconducting gap in function of the frequency. With the Kurt-Ferrari model, using a constant mass parameter, we see that agree with the later case with a small superconductivity, but an increase of the superconductivity, how large is the chemical potential. But using a Kurt-Ferrari propagator with the running that I showed before in the presentation, the superconductivity become more relevant. But if you increase the chemical potential, this relevance starts to decrease because of the influence of the couplings that I showed you before. So that's the result of the superconducting gap for the chemical potential. That's the result in a log scale. So you can see that all the models did present relevant superconductivity to the small chemical potential, but how large is the chemical potential? The Kurt-Ferrari model with the running, that's the green line, present more relevance because of the strong influence of the running couplings, but the RGZ also has a very large increase with relation to another constant model, that's the blue line. And how large is the chemical potential, to extreme chemical potentials, we can see that all these models present a superconducting gap that increase in function of this parameter. So some information that we get from this analysis is that the color superconductivity through this toy model is sensible to this non-perturbative gluon mass. Also, we can see different kinds of the superconducting gap and how these different kinds behave with the chemical potential. Each kind of confining model has a specific behavior. For a large chemical potential, all these models agree with the increase of the superconducting gap with the chemical potential. And the complex polars and other complex structures from the confining propagators does not lead the unphysical results. That's something good. And as the natural step, we are investigating the natural extension of this toy model using abelian gauge fields in a KCD spider model. And in future work, we're thinking also to explore a scenario with the strong magnetic fields. That's why I am here seeing a lot of good talks in this conference. So thank you so much.
Okay, thank you. Questions for João?
I have a very naive question regarding the assumptions about the gluon properties at high densities. Naively, if you increase the density sufficiently high, you would expect deconfinement and there will be no gluon mass, nothing. So at a minimum, I believe you would have to consider that mass to be density dependent. Is that a reasonable thing to think about?
Yeah, I think that is reasonable because if you increase too much the chemical potential, the asymptotic freedom will generate this kind of phenomenon. But we are interested in a kind of range of the chemical potential where the confinement effects are relevant. So we are trying to explore this part of the results where we see that there are different behaviors to each confining propagator.
This mu is quark or baryon chemical potential?
No, it's the quark chemical potential.
But 500 is probably already sufficiently large that you definitely should have deconfinement.
Yeah, one of the suppositions of this work is that even with a very quiet chemical potential veil, we can get some kind of the influence of the confinement. that we exchange this parameter to see how the effects of the confinement can affect the superconductivity.
Okay, thanks.
Other questions?
Hi. So I suppose that the qualitatively your results should be somehow similar to the analysis by a non-local NGL model, right? Because gluon propagator is a massive propagator, and so deep infinitively. And so have you ever considered some comparison to the non-local NGL model results?
That could be a possibility to a model to explore. But I think that the idea exploring the UCAL model should be the same that using a non-local model, the NGL model, because in some sense, here, integrating out the gluon fields, we get in this kind of the action that we have a kind of the non-local model.
Yes, that is actually my point. And there are actually in the market, there are many computations using a non-local NGL model. And so I think that the qualitative or even the quantitatively, there must be some consistency. So have you ever checked some literature or some?
Okay. No, that's now I understood your question. Now it's a really good point. Okay. Yeah, I didn't think about this. Because in some sense, there are two non-local models now. Okay, I didn't think about it.
Okay.
Okay, if there are no more questions, let's thank João again. Let's see, our next speaker is Jose Jimenez. I still don't know the title.
Yes.
I'll tell you when you have 5 minutes left.
Okay. Hello, everyone. Thanks to the organizers for the opportunity to share my recent work. Today, we are going to study the fundamental mode oscillations, radial and non-radial, of the so-called vector MIT back model, manifested as strange stars. Okay. The outline is I'm going to present a motivation, then develop the thermodynamics in order to construct the equation of a state, then summarize the main ideas about the structure, the hydrodynamic structure of these stars, and then summarize some ideas also about the oscillations, the relativistic oscillations. Finally, I'm going to present my results. So the problem begins with this kind of studies that appeared more than a decade ago, where people try to build the equation of a state for neutron star matter, and what they do is to interpolate between PQCD and chiral effective theory, so they build these bands, and interestingly, one can see that the bands satisfy these astrophysics constraints if you allow the equation of a state to be very stiff. So maximally you can get 0.8 values of the speed of sound, near to the causality limit. So apart from that, we know from this LIGO event about the spiral phase that these neutron stars had a spiral phase and they emitted gravitational waves and they were detected. We don't know exactly what is the signal at a collision and in the ring down. Okay. However, apart from knowing of the existence of neutron stars, we can also have to remember the existence of strange stars based upon this hypothesis, Bodmer-Witten, which tell us that there could be that strange matter is more stable than neutron matter because we can have that the energy per baryon is less than that of iron. So if we combine a lot of strange matter, we can build what is called a quark star, which is a quark star made of more or less 95% of quark matter, and in the other cross you can add some hadronic mantle, which is very different to the usual neutron star idea, right? Because here people have done numerical simulations in numerical relativity where they have compared the gravitational wave emission between an strange star, usually created with the MIT back model, and this LS, Latimer-Sweaty equation of state, which is hadronic. So you can see that more or less the behavior is somewhat similar in the spiral phase. There is these peaks, and there in the ring down, one could differentiate. So we don't know exactly about this phase, and in principle, the gravitational wave observations could be coming from strange stars. Okay, and another interesting property that was measured indirectly by people working with LIGO was the so-called non-radial F modes, when the two strange stars are orbiting one between the other. We can realize that there will be some kind of oscillations, deformations in this star, and this could be related to the tidal deformability. Focus only in the one, okay? So we have to focus in this red curve, orange curve, and green curve. And we can see that more or less the frequency of these non-radial modes is around 1500 kilohertz or 2000 hertz, more or less, okay? However, these studies did not consider anything about strange stars, so we wanted to study this possibility within the so-called MIT vectorial MIT back model, because we have the system of quarks, up, down, and strange, and we can add a repulsion term, which will make the equation of state to be stiffer. So we will get high values of speed of sound in agreement with these interpolations found by Anala and other people, okay? Focus more or less in the intermediate sector of densities. And we can build this model. We can apply the mean field theory approximation, and everything is more or less similar to these models. We can build the Hamiltonian. We can obtain the spectrum. We can get the energy density of the system. And of course, we can use thermodynamic relations to get the equation of state, pressure versus energy density. And we have to fix parameters. For instance, this GV, which is the division between the coupling, the vector coupling between the up quark and the vectorial term, and the mass of the vector field. And there is another coupling, XB, which we fix as 1 in order to produce more massive strange stars, okay? And we fix the masses as this, and we vary the values of the GV constant. We can build the equation of state, and we can see that the speed of sound surpasses the conformal limit of 1/3. And you can see an increasing behavior in agreement with these findings from Anal and other people. We can build the mass-radius relation, the mass energy density, but our focus is to study the stability of these objects. So usually, one has first to solve the radial oscillation equations, where one can define Lagrangian perturbations of the whole star when it is oscillating. These perturbations are key, which is delta R over R, a deformation of a volume element of the whole star, and this delta P, which is a change in the pressure at some position in the star. And we have to obtain this omega square, which, putting all the profiles coming from the Tolman-Oppenheimer-Volkoff equations, we can obtain a relation between omega square and the central energy density. We can find this nu zero, which is the frequency of the fundamental mode. And the importance of this mode is that as long as this quantity is positive, the stars are stable, okay? So it is easy to verify that these values of mass, 2.2, 2.4 more or less, coincide with this maximum, the usual criteria of one-phase stars. One can also calculate the period, okay, the period of oscillation, assuming that there is no viscous forces. And now the complicated part comes when we build the non-radial case, because now the Schwarzschild space-time element is not as the usual Schwarzschild that we know. There will be a combination of harmonic spherical harmonics, this function H0, H1, and it is far more complicated. So there will be more displacements in the radial direction, theta direction, and phi direction, okay? For these functions, W, V, V, okay? And there are a lot of equations to be solved here. Okay? This is the case when we are disturbing non-radially the star, and also the space-time is oscillating. So it's far more complicated because usually people apply the so-called Cowling approximation where the space-time doesn't oscillate, only the fluid elements within the star. Okay? We have done the two cases. The difference is more or less 5%. And we have also to solve equations for these oscillations outside the strange star, the so-called Cerilli equation, which is more or less a Schrödinger equation. We define these tortoise coordinates, which depends on a potential, which comes from these terms, and this f of r function. And then we can get that the non-radial oscillation frequencies in the fundamental mode is more or less as that found by Praten in collaboration with LIGO. But we are now only plotting this against the normalized mass. M0 is the solar mass. And we can see this behavior, this increasing behavior. Normally, neutron stars decay, okay? And you can see this in this plot, right? Hadronic neutron stars decay, but strange stars start to increase, okay, as we increase the mass. We can also calculate the damping time, which means that this star will be oscillating non-radially, emitting gravitational waves, and these gravitational waves, in principle, could be correlated to the ones observed by LIGO, for instance. And this serves us to more or less infer the macrophysics happening within these strange stars, okay? We have changed this GV parameter, okay, which, as I told you, produces stiffer strange star equations of state, okay? Usually, this is not the case because people use the MIT Bach model, and in this model, the speed of sound is always less than 1/3, okay? But in this case, we are surpassing this limit, so these are very stiff strange stars. Another interesting thing that we can do about these stars is to build a so-called universal relation. Normally, if you have participated in some seminars about neutron stars, you can hear these universal relations between, for instance, I log Q. Inertia moment, this lob number, and this quadrupole moment, okay? But this is all about the static parameters related to the star, but we can also relate this frequency, this non-radial frequency, to the average compactness of this star, okay? You can see that if you add the 4 pi, you can have some kind of density, constant density, right? Density is mass over volume, right? And we have verified that these three parameters, A and B, have this kind of ranges. For instance, for each value of the parameters, 0.3, 0.4, okay? We found that the V values coincide with some works that they have studied for neutron stars only. So they were not interested in the case of strange stars. However, this A is different. It's different compared to the ones for hadronic neutron stars. So this is interesting because we are developing another kind of universal relation for people observing strange stars to redefine their observations in order to differentiate these strange stars from neutron stars. And you can see here the behavior of this universal relation, the non-radial frequency mode, fundamental mode versus this kind of constant density. And you can see that this is a line, right, for all these values. Of course, there will be some relative error. The percentage is more or less 15%, which is usually in this kind of universal relations. Okay? So we have used the vectorial MIT Bach model in order to introduce repulsion or stiffness into the strange stars. Okay? We found that the parameter, when this is increasing, it stabilizes stars within this range, and below it has the opposite effect. You can see this in the plot because the frequency is increasing. And about the non-radial F mode, we can classify, okay, this kind of ranges, 1.6 to 1.8 kilohertz for high mass stars and 1.5 to 1.6 kilohertz for low mass stars. LIGO could detect in the future all these kind of stars. We have presented a new universal relation, okay, not existing until now for many models of strange stars. And now we are working to include strong magnetic fields in this vector model in order to verify if this universal relation is kept or maybe could change. So in this case, we have to define another way to build these universal relations. Maybe not with the average density, but using another properties, maybe inertia moment or something like that. Okay? So that's it. Thank you.
Okay, questions for Jose?
So in astrophysics, there are many different kinds of university relations are known. And so you also this university relation insensitive to the equation of state. Is this somehow related to the, for example, the I love Q relation?
We have not verified because usually these people, I love Q relations are only based on the structural properties. We are now disturbing the whole star and we are getting oscillation properties. So this is different.
Yeah, but somehow that oscillation property is also characterized by the somehow how easy the star can deformed or something, right?
Yeah.
And so in some sense, I can imagine some relation, but
yeah, we were thinking about this kind of universal relation because there are many works in the literature working with this kind of universal relation for neutron stars and few ones for strange stars. So we don't want to present a highly new universal relation. Maybe in the future we are going to work with this.
Okay.
What you say, relation between this F and I love Q or something like that.
Yeah. Okay, thank you.
So Jose, you've shown that the speed of sound goes up above the 1/3 limit. Does it go back again, or does it keep going?
Yeah, in principle, it should go back, but we have to include more terms here, but our maximal mass stars end here, more or less.
But if you keep this and go on, it's going to become superluminal, right?
Yes, so we should add some terms that will make this equation of state softer in order to then approach to PQCD.
Okay.
Okay, last questions? Everybody wants coffee, so I think we have coffee break for 30 minutes. So thanks to all the speakers so far, and we'll be back in a half hour.